Hello, ENET 130 at Bellingham Technical College. We're continuing our study of semiconductors and semiconductor circuits. This is recorded lecture number 10, and we're continuing our discussion of bipolar junction transistors. In our previous lecture, we went over the material science that makes up a BJT, or bipolar junction transistor. We discussed how it has 3 different layers of semiconducting materials, 2 P's with an N in between, or 2 N's and a P in between. We discussed how the thin, lightly doped base is key to making it work, and discussed how it was different than just 2 diodes back to back, and touched on the concept of current gain, and being what a BJT basically is all about, and then went on to discuss how Kirchhoff's current law operates, relating emitter, collector, and base currents. And now we're ready to dive into our gain parameters. And just to recap, the magic of a BJT is it's a current gain device. So if we put a little bit of current into the base, we can control and dictate how a larger amount of current can flow between the collector and the emitter. And so our first performance benchmark actually is relating those. So the one that you're going to see fairly frequently is beta, and that's the ratio of the collector current to the base current. So you can think of a bigger beta being a bigger gain. So the bigger the beta, the more collector current we enable that transistor to carry for a given base current. So if I have a beta of 100 and I put in 1 microamp into the base, I can get 100 microamps flowing through the collector. Now, obviously, since the collector and the emitter have pretty similar currents, we can approximate that as the collector emitter current being about 100 microamps. So that's basically our current gain ratio. We've got another performance parameter defined, alpha, and that's the ratio of collector to emitter currents, which, basically if the base current's approximately 0, alpha is going to be pretty close to 1 in that case. Beta tends to be huge. It's not unusual to see betas of around 100 or 200, and in fact, if you aren't given one and you find you need to approximate it, 100 is not a bad number to shoot for. Now, we can relate beta and alpha and collector and emitter currents to each other 6 ways from Sunday by just invoking our Kirchhoff's current law and the definitions of alpha and beta. So we can derive all of these relationships just using these definitions and our current conservation of current relationship through the transistor. You might need to do this to answer some problems. Perhaps you're given alpha, you don't have beta, or you've given beta and you need alpha. Basically just remember the definitions. These you will have to memorize because they do mean specific things, and when you see them in a spec you have to know how to apply them. But having said that, if you need a relationship between any of them, just go back through Kirchhoff's current law and apply a little algebra with a little math. Symbols. This is the standard circuit symbol for a bipolar junction transistor, a BJT. And the trick is to remember that the arrow always points in the direction of conventional current flow. So this is an NPN schematic symbol, so we know that conventional current will flow from the base to the emitter. And that makes some sense because we've got the base is the P material, so if we have positive current flowing into the P, that's going to bias the base emitter junction forward, which is what we need to operate the transistor. I'll point out there is a little typo in your textbook for figure 4.9, the figure caption. This should say PNP. Mr. Fiore is showing us the difference between an NPN and a PNP symbol. So this lower figure is a PNP, so in this case the conventional current flows from the emitter to the base, and the arrow is showing us that. Okay, next we're going to look at how a bipolar junction transistor looks to a circuit in terms of what is the voltage drop over it versus the current through it. And in this case, we're going to talk about current flowing through it from the collector to the emitter, because that's the controlled signal, the big pipe. That we're the base current and the base voltages, it's basically just our little valve we're turning. So we're going to look at the main pipe here. And we're going to be looking at current flowing through the transistor for this next discussion, emitter to collector. And we're going to be looking at what's the voltage drop from the emitter lead to the collector lead. What's the delta V? Because when we do circuit analysis or we're designing a circuit, we want to know the voltage current relationship through any device. I mean, for a resistor, it's pretty easy. The voltage drop is always equal to the resistance times the current flowing through it. We're going to look and see what kind of analogous relationship we have with a transistor, and as a hint, it is certainly not as simple as what we'd have through a resistor. Of course, which is a good thing, because we are relying on that more complicated relationship to do a lot more things in a circuit for us. So let's take a look. Okay, in order to have any kind of discussion about current voltage relationships between the collector and emitter in a transistor, we need to look at a series of curves. There is no one relationship. This is analogous to somebody asking you, if you're a chemistry student especially, what temperature does water boil at? And your first response should be, well, what pressure are you talking about? Because your boiling point depends on your pressure. So water boils at a much lower temperature if you're at the top of a really tall mountain than at sea level. In the same way, the relationship between your collector current and your collector emitter voltage changes depending on how much base current you have flowing in. It's kind of like that third variable. And in this case, it's analogous to saying, how wide open is the valve that's controlling my collector emitter current? So the more base current you give, the bigger a pipe you make for collector emitter current to flow, and the more current you'll get with any kind of applied voltage between the collector and the emitter. So we've got a tunable relationship here, and our figure 410 walks us through what that is for various different base currents. So let's check this out. So we've got collector current on the Y, and given that base current's pretty small, this is the collector to emitter current transiting the transistor. This is the controlled signal. And we have collector emitter voltage on the bottom. So there's just like the voltage drop over the device, just like we talked about in DC. And these curves, these green curves, are each separate plots. So somebody went in the lab and they took their transistor and they put across it a variable voltage supply like their DC power supply, and they put a shunt resistor in line with it, and they measured the current, and so they kept turning the voltage up between the collector and the emitter, gave it more voltage on the x-axis, and plotted these curves. And they got a different plot depending on how much base current they were giving the device. So we're going to start with this lowest curve, and I'm going to use a red to kind of trace over it. So if they left the base lead unconnected, just open, they would get just this little tiny flat line that was almost zero, like almost no current flowing between the collector and emitter, until they got to this value, base current open B V sub CEO, and what that is basically the collector to emitter breakdown voltage. So you've got to apply something here that's going to kind of destroy the device before you get any current flowing through it. And what that's telling us is that if we don't apply base current, we can't get any current flowing through the device. And we can see that in our beta relationship, right? So we could multiply both sides of this equation by IB and say my collector current's going to be beta times my base current. Well, if my base current's zero, 0 times anything is 0. So I'm not going to get anything, or I'm not going to get much. In fact, I'll get a little bit of tiny current that's just mainly due to intrinsic semiconduction properties, and that's this ICEO, meaning OO for open base, and that's basically sort of this sort of residual leakage current that you can get through the device. So that's the most you can get if you don't feed the base with current, because you basically haven't turned the device on, so to speak. Okay, so what if we give it a little bit of base current? Let's turn the transistor on. We're giving it, say, 10 microamps of base current. So now we got base current flowing. So now we're going to turn up the voltage between the collector and the emitter, and we're going to measure the current that flows into or out of the collector, depending on whether we have PNP or NPN. And this time we're going to get some current flowing almost immediately as we start to apply voltage collector to emitter. So this is great. In fact, it's even steeper than the relationship we would get with a resistor. But then we're going to get to a point where if we keep turning the voltage up between the collector and emitter, we don't get any more current. And in fact, we get almost a flat line where with the same amount of current flows regardless of how much voltage we apply collector to emitter. It's a flat line, kind of like an ideal current source, just doesn't really care until we again get to the breakdown voltage, which we're not going to get anywhere near because we're going to use a proper current limiting resistor. This is bad. We don't want to go beyond there. But we've got this beautiful region in here of constant current. But we also know we're not going to get any more current no matter how much we turn up the collector to emitter voltage. And in this way, a bipolar junction transistor is very different from a resistor. So we've got high current increase as we turn up the collector to emitter voltage very early, and then almost a flat line. Okay, well, doggone it, but say I needed more current than this, whatever this was. Say I needed a higher collector current. How do I get it if I can't depart from that red line? Well, what I have to do is turn up my base. And so I would jump to the next line. So each one of these plots represents an increasing applied base current. So say I apply 20 microamps to the base. Well, now as I turn up the collector emitter voltage, I can access this higher curve. So now I can get a higher maximum collector current because I put more current into the base and I enable the transistor to give me more current. So these are characteristics that are inherent to the transistor itself. So we're looking at the action of increasing base current. Each one of these curves is a different I base, and they're proportional. So when you look at a spec sheet, I base 1, I base 2, someone's already done this. Maybe in the quality lab of a semiconductor manufacturer, somebody's already measured all these things, and they've captured it in the spec sheet. But this is very, very typical behavior of a transistor, and it's in fact what we count on. So the higher the base current, the higher one of these curves that you can access. And we also have a few benchmark names. We got some vocabulary going here. Okay, so this dashed line that represents these little knees where your collector current heels over and follows the flat line, that's called V collector emitter saturation, VCE sat, and you will literally see this term on a spec sheet. So that says that's how much voltage I have to apply collector to emitter to start entering this flat region where I might want to operate if I'm operating my transistor like a switch. B VCEO is my breakdown collector emitter voltage, and it doesn't really care what the base is, not too much, so that's one to watch and that's one not to exceed. And then the ICE base open, that's the most current you can get if you don't apply a current to the base, and it's going to be teeny tiny, kind of analogous to the reverse saturation current in a diode. Okay, so 3 vocabularies, but most important, we can get more collector current the more base we put in, and it's a known function. Okay, going through all of these, you can walk through our figure 411, an example where Mr. Fiore gives you an example of how to use this a set of collector curves. I'll just walk through this verbally very briefly. So you have an unknown bipolar junction transistor, and you've applied 30 volts base to emitter through those two leads, and you're measuring a collector current of about 4 milliamps. So you're with 30 volts. So you're kind of operating on this point of the curve, a little bit over 4. And somebody gives you this set of curves. You know something about the transistor, and you want to know what the beta is, because you might use that gain factor. Beta is a gain because you want to design a circuit. And you know that each one of these curves represents an increase in 10 microamps per trace. So you could use your single measured point here to back out beta from these experimental curves by just simply saying, okay, I've got a collector current, and I know that beta is equal to my I collector divided by my I base. So I have an I collector point that I just measured in the lab, and if I only knew what base current would have given me that and put me on this curve, I could have my beta, and then I could use that in a circuit design. Well, I'm told that the base current is increased by 10 microamps per trace. So I have 0 down here, and then I have 10 microamps here. Again, I'm using someone else's set of experimental curves, 20, 30, 40. Okay, so I had to have applied during my measurement. I had to have applied, or I couldn't have measured that. I couldn't have gotten that 4 milliamps out of the collector. I must have been applying 40 microamps. So I know IB was 40 microamps. I know my I collector was about 4 milliamps, maybe 4.2. So I just divide those, and I get a beta of 105, which is fairly reasonable. This next section, rise in beta and early voltage, just basically gives a little qualitative discussion of why these flat regions aren't quite flat. It's not just ohmic response, it's not just the transistor acting with a bit of ohmic resistance. It also has to do with the widening of your PN junctions as you apply more voltage collector to emitter. Not all that important for what we're going to do in using transistors and circuits. Okay. Next, we kind of alluded to the idea of a lot of the components on our curve traces, our collector current versus collector emitter voltage traces being specs. These are inherent characteristics of the transistor you buy. So let's take a quick look at a typical bipolar junction transistor data sheet, because a lot of those key values are ones you're going to be looking to your spec sheets to get and relying on that. Okay, so here's one for a typical transistor. This is an NPN silicon transistor. So one of the most useful things you might want to look at is the construction and the lead arrangement. A lot of transistors have a low current plastic package. It's flat on one side, and that flat is really nice because it gives you a lead orientation that you can relate to what's the base collector and emitter, because you have to know that to use it in your circuit. Now obviously maybe you turned it around wrong. You know, these specs are very reliable generally, but you might want to confirm it. So just remember, you've got two PN junctions, one between the base and the collector and one between the base and the emitter, and you can always confirm what you're seeing in these diagrams by using your ohm meter and seeing which one will conduct and in which direction. So that's where you're going to remember that from the standpoint of lead identification, you can view those two PN junctions like two little diodes. So I'll leave that up to you to think about what signal from your ohm meter you would get to confirm the leads, and how you might write up a procedure to do that if you had an unknown package and maybe didn't have a spec sheet available. That's something you should be able to do in a really useful skill. But assuming you've identified your leads, move on to the first thing that you're always going to check before you plug one of these semiconducting components into a circuit, or any component into a circuit, is maximum ratings. So these are things that keep you safe, keeps your component from blowing up, from melting, from starting a fire, and more importantly, it keeps your component from working in a way that you wouldn't expect. So you can have components fail and not necessarily explode or give, or smell bad, smell hot, and they're still not working properly in your circuit, and then your circuit won't work, and then maybe you can't do your job. So the silent failures can sometimes be just as bad as the smoke and blue spark ones. So we want to make sure that we design around these maximums before we even look at the performance parameters that are going to give us what we want. This is what not to do, is in the maximum ratings. So maximum collector emitter voltage. This is that VCEO, 40 volts. Don't put more than 40 volts collector to emitter. So when you look at your supply voltages, your VCC and your VEE, make sure you adjust those so you can't get more than 40 volts, or you could destroy the device or make it behave unpredictably. And you're going to have you're going to have similar upper limits for collector base and emitter base. So across every one of those junctions, and notice emitter base has a much lower maximum. So be respectful of that. Current maximums. We talked about wanting to get a big collector current and using a higher base current to get it, but there's such a thing as too much of a good thing, and that too much of a good thing is 200 milliamps DC equivalent. So that's the most collector current you're going to flow through the device. So I don't care what your beta is and how much base current you give it, don't try to flow more than this, or your device won't work or might melt. And related to that is your total power dissipation, which is not necessarily going to be these two numbers multiplied. Notice if you multiplied the max collector emitter voltage by the max collector current, you'd get 800 milliwatts, but the device doesn't want to see more than 625. So that's another number you have to respect when you design your circuit. The product of your actual voltage and current flowing through that device better not exceed 625 milliwatts. Okay, so having defined what not to do, let's look at the cool stuff the transistor can do, and that's mainly encompassed in our beta. And remember, on a spec sheet, beta is usually given with a term H, small h with a subscript FE. So this is beta. So the first thing we'll notice is beta is not constant. Again, we see it depends, right? So if you say, well, how much gain, current gain, can I get out of this transistor? The spec sheet's going to say, well, how much collector current did you want to have? And what collector emitter voltage did you want to apply? So the spec sheet basically assumes you're applying 1 volt DC collector to emitter, and then it gives you either a minimum or a range of betas depending on how much current's flowing. And you can see that your betas for really, really low collector currents are 20. It's still respectable. It's an order of magnitude gain, but nothing fabulous. And likewise, if you're asking the device to give you a lot of current, it's again your betas are modest. But in the middle, you get some pretty screaming high betas. And so when you see something in a problem or some kind of project description where you're asked to calculate something about a transistor circuit where you're given a beta, chances are it's going to be that beta under ideal operating conditions. It's going to be this maximum beta. And even for a given collector current, check out the range. This is one transistor, one temperature, one collector current. You could have a beta that really floats anywhere between 50 and 150. Wow, That's a big change in gain. That makes it hard to design a circuit that is reliant on the transistor gain. And because of that inherent variability in gain that is a product of the manufacture of the semiconductor device, that material science, we have a whole array of amplifier circuits that take advantage of these transistors, excuse me, that are designed to account for that variability in beta. Still make use of it, still give you that gain, but cancel out the variability somewhat so that we can still get the amplification we need without basically having our entire circuit output fluctuate with beta. So we'll get into that in what we call common mode amplifiers. But just remember that the need for some of those designs started with this big old wide variation in beta. So as if it wasn't bad enough that our beta varies with collector current, it also varies with temperature. And the variability is so significant that one of the things device manufacturers give us is a little chart. So this is a chart of what's called normalized beta, or HFE, depending on both collector current and temperature. So normalized means everything's normalized to a 1. And so you can compare what your beta would be for low temperature to high temperature and for low collector current to high. And this is a log scale plot. So you can check out some numbers. For instance, if I had a collector current of 2 milliamps right here, I would have a beta of around 0.4 normalized at negative 55 C. So if I'm operating my circuit, say, outside in the winter in Canada, I'd have some normalized beta of 0.4. And then if I brought that same circuit inside into room temperature, use the same exact collector current, my beta would just about double. And then if I took that same circuit to Phoenix and put it on a roof and let the sun beat on it in July, I'd get yet another doubling in my beta. So I would hope that I design my circuit to account for that. Okay, last topic of this lecture is the Ebers-Moll DC model. And that's to account for how do we actually use transistors in circuits. How do we design a circuit around it and analyze? Because we got a lot of nice stuff. We got some precautions, but we've got this fabulous device that can give us a constant current under certain circumstances, that has this particular relationship between base current and collector, and has this crazy steep slope, then a plateau in the current voltage relationship. And it's a little tough to account for all of that in what's a voltage drop going to be somewhere in a circuit, or how much current am I going to have flowing through one part of the circuit where I have a transistor. An example of this is figure 4.15. This is a very simple amplifier circuit that uses a bipolar junction transistor. And it's just the circuit symbol. It's nice. We know we're going to have base current flowing in the base, and we can tell that this VCC is our bias on the collector. We're going to have collector current flowing through R sub C like this. We're going to have base current flowing in like this, so emitter current's got to flow through there. But how do we model in something that we can do some calcs on, some calculations, everything that's going on inside this transistor? Because we know we can't just treat it like a resistor, we can't treat it like a capacitor. How do we basically replicate those crazy voltage current curves in a practical circuit? So the way we do that is to use a model. So we take everything in this dotted circle, this whole transistor, and we represent it with this thing, which is something that we can use. So this is known as the Ebers-Moll model of a bipolar junction transistor. So this is not the transistor. It is a representation of it that models, that produces the same current voltage behavior that the actual semiconductor device does. And this allows us to model our circuit, to make calculations, or to design a circuit that will work with a real transistor. So let's check out what components, what parts we have here. Not surprisingly, well, let's start with which ends are which. So we have the collector end up here at the top, and over here at the side we have our base. So these are connection points that are representing our leads in our real transistor. And then down at the bottom we have our emitter, and this would be pretty much the same regardless of what type of transistor we had. So not surprisingly, we are representing the connection between the base and the emitter with a diode. So we're representing the base emitter junction, the PN junction, with a diode, which is kind of where we started when we talked about the semiconductor roots of a BJT. So that's cool. We know how to work with a diode, right? It's basically like a little voltage source that pushes back in the direction we're trying to flow current. So this would be like a little 0.7 volt source with maybe some resistance. Maybe not. The main magic, though, that takes us from being just a diode to being a transistor model is a current source. So remember, if you have a circle with an arrow in it, this is an ideal current source. And it's going to provide us with a current that's equal to whatever current we put through the base, we pushed into the base, times our beta. So that's where we pick up the transistor characteristics from the spec sheet. So this is our HFE. So this current source is going to give us, it's going to establish whatever voltage collector to emitter is necessary to give us whatever collector current we've asked for based on the base current we gave, the current we gave at the base current, and the beta from our spec sheet. And that's how collector to emitter voltage is established. Remember, a ideal current source requires whatever voltage it needs to give you the current you asked for. So this is how we're going to model all of our bipolar junction transistors in some circuits, and this is going to allow us to do calculations about current flow and voltage drop and walk our way around circuits and design circuits to do what we need later on in amplifiers. So if we took this Ebers-Moll model and we plopped it right in this circuit inside the little dotted circle, we'd have something like this. And I'll go ahead and dot around it. So here's the transistor in the dotted line. Here's our model. All the way down to E. So this stuff is basically representing the function of the transistor. So between point C and point E, we can measure a voltage difference, VC to E, voltage drop. So we have our constant current source. We know how much current it's going to give us, depends on the beta, and we're going to establish the IB depending on what voltage source is here, how big our resistor is. We know we're going to have a 0.7 volt drop going from B to E because we've got presumably a silicon based transistor, so this is going to have 0.7 volt forward bias. V forward takes our toll in voltage like any diode would, and away we go. So now we can apply Kirchhoff's voltage law to the base emitter, and then once we've figured that out, we can go on and use Kirchhoff's voltage law, collector to emitter, and usually solve for this. So that's what we will do in our next lecture. We'll apply our two big KVL loops using the Ebers-Moll model for our transistor for different betas. We'll examine different conditions under which the transistor operates, and we'll find that there's some cases where beta doesn't matter, that the external circuit becomes limiting in VCE and the IC that we can get. So sometimes we're operating in an area where the beta is limiting how much collector current we can get, so it's transistor device limited, but other times it's external circuit limited. So we'll point those out as being two different regions of operation, and we can deliberately place our circuit in either one of those to get the output we want. So stay tuned for the next lecture. We'll take up those topics and finish out this chapter.